Welcome back to the deep dive. Today we are wrestling with, I think, one of the most critical issues of our interconnected world. It's something that has pretty rapidly moved from being a philosophical footnote to a hard, critical design and safety requirement.
Yeah.
We're talking about trust in artificial intelligence.
And that's such a crucial framing.
Yeah.
Because for years, AI was seen mostly as this technological achievement.
Right, a feat of engineering.
Exactly, a feat of computational power. Now it is so quickly shifted to being a critical societal force. It's deeply integrated into our daily lives, influencing decisions in, well, everything from our credit scores to medical diagnostics, even predictive policing.
The sources you shared really hammered this point home. I mean, when a machine is making these consequential decisions, trust is no longer a soft, feel-good metric. Right?
No, not at all. It's a necessary condition for public safety and just public acceptance.
So our mission for this deep dive is pretty straightforward. We're going to try and navigate that really treacherous space between blind faith, where we just accept whatever the machine says.
Which is so dangerous.
So dangerous. And on the other side, total skepticism, where we just reject these valuable tools entirely. We're looking for that sweet spot, calibrated trust.
Calibrated trust.
Yeah.
It's where our reliance on a system, a human's reliance, aligns precisely with the system's actual, verifiable capabilities.
So it's about knowing when to trust it.
Exactly. Knowing when to trust it completely, when to double-check it, and crucially, when to just override it and say, nope, not this time.
And to get there, to build that foundation, we first have to recognize the ethical pillars that really all responsible AI development has to be built on. These are like the non-negotiables.
That's right. We're talking about transparency, fairness, accountability, and robustness. And these aren't just buzzwords, They represent very specific technical and organizational requirements.
Okay, let's break those down just a little. So transparency is?
So we can understand the path to a decision. We can see the how. Fairness, to make sure we get equitable outcomes, regardless of, say, demographic factors.
Accountability.
So we know who is responsible when the system inevitably causes harm.
Which it will.
Which it will.
Yeah.
And robustness, making sure the system performs reliably and safely, under stress and all sorts of real-world conditions.
These four principles are absolutely key. And the discussion really requires us to acknowledge that without a really rigorous commitment to them, the stakes are just enormous.
There's systemic risks.
Yeah.
Without that commitment, you're looking at algorithmic bias, just amplifying the inequalities we already have.
Right.
You're looking at decision-making processes that are so opaque they can't be audited by regulators.
Yeah.
And autonomous behaviors that can lead to these cascading unintended harms.
So eroding public trust isn't just a PR problem for big tech.
No, it can fundamentally undermine the institutional and infrastructural fabric of our society. And that's why designing for trust is, well, it's paramount now.
Okay, so let's really unpack this challenge. We can look at three sort of structural forces that are inherent in modern AI systems, the ones that actively erode the kind of traditional human-human trust we're used to.
These are the built-in hurdles we have to overcome.
Exactly. And we have to start with the obvious one, but one that's getting more and more complex, the black box.
Right. The black box AI problem. I mean, it's the foundational issue in modern systems, especially with deep learning.
So what does that mean today, in simple terms?
Simply put, it refers to systems where the internal reasoning, the statistical weightings, are hidden from view. They can produce results with incredible, sometimes superhuman accuracy.
Yeah, that's the seductive part.
It is. But they fail to offer an interpretable path. There's no trace for how that reasoning was reached.
We often think of the black box as just being, the complicated math happening inside a deep neural network. But what the sources reveal is that modern systems have actually made this problem worse. They've added new layers to the mystery.
That's a great way to put it. It's not just a single locked door anymore, like a vault with multiple combination locks.
So it's not just the complexity of the model itself.
Exactly. It's no longer just the deep, complex layers of statistical relationships learned from massive data sets. Today, you have large language models, LLMs, and they introduce this inherent complexity because their outputs are so highly dependent on subtle changes in the prompt.
Oh, yeah, I've seen that. You change one word.
You change one word, you shift the context window, you tweak the model's internal temperature settings, and the whole reasoning path changes. It's fundamentally non-deterministic.
So the logic isn't fixed, it's fluid.
It shifts with the context. And that makes simple reproduction or verification or even just debugging incredibly difficult.
And then you add another layer on top of that with agentic systems, right? The ones designed to take action.
And the problem just compounds. Agentic systems obscure their logic because they're designed to go out and retrieve external information. They run tools to execute tasks, and they maintain this internal state or memory that might not be fully observable by the organization that deployed them.
Especially with something like ARG, which I want to touch on.
Yes, especially with ARG or retrieval augmented generation.
Okay, so let's just pause there for a second. For our listeners, what is ARG and why does it make this inspection so much harder?
So retrieval augmented generation is a pretty common technique where an LLM doesn't just rely on its base training knowledge, it actually goes out and searches a specific external database, like a company's internal documents, for example.
A proprietary knowledge base.
Exactly. It finds information relevant to your prompt, and then it synthesizes its answer based on that retrieved information. The problem is that retrieval step is external. It's context-dependent, sometimes it's proprietary.
So if the database is bad,
If the system retrieves bad or outdated information, the output will be flawed. But tracing that fault requires you to inspect an external data flow, not just the model's internal weights. It makes the whole system so much harder to inspect and govern.
which means this opacity isn't just a technical curiosity, it's a massive governance failure point.
It is. If you cannot audit precisely how a system reached a decision, let's say denying a loan or flagging a patient as high risk, you lose the ability to detect when its behavior subtly changes over time.
And that's what's called model drift.
That phenomenon, yes, we call it model drift. It happens when the real-world data the model starts to see begins to differ statistically from the training data it learned from. And when behavior can't be easily inspected, these subtle changes are so hard to catch.
Which puts safety and oversight and compliance at severe risk.
Immense risk.
And here's where it gets, I think, really interesting. Because sometimes the model looks like it's working perfectly, but it's actually succeeding for all the wrong, fragile reasons.
Yes.
This leads us to a specific and really counterintuitive failure mode that this opacity hides. Shortcut learning. It's often called the clever Hans effect.
This is such a textbook example of these hidden failure modes that just undermine dependability. Shortcut learning is when a model performs extremely well in testing.
It aces the test.
Aces the test. But it does it by exploiting irrelevant accidental patterns in the training data, a shortcut, rather than actually learning the complex intended task. So it looks highly accurate on its training data, but it's operationally fragile because that shortcut often disappears in a new real-world environment.
And the sources provide a really terrifying real-world example of this from healthcare.
They do.
AI models were trained to diagnose COVID-19 from chest x-rays, and they achieved super high accuracy in the training environment. But it turned out they weren't identifying the medical features of the lungs at all.
Not at all. No, they were identifying things like clinic-related annotations or metal markers on the image.
Wait, like the text written on the x-ray?
Exactly. Things that indicated which hospital the x-ray came from, or even the type of machine that was used. Essentially, the AI learned images from Hospital A are 80% likely to be COVID cases.
Because Hospital A was a major COVID treatment center in the dataset.
Precisely. It happened because COVID-positive cases in the training data were just more likely to have been annotated by doctors in a certain way or collected on certain machines. So the AI was brilliant at identifying metadata.
Not medical pathology.
Exactly. And until that model was deployed in a new clinic that used different annotation standards, nobody realized its supposed medical expertise was based entirely on image metadata and correlations, not radiological science.
So the model appeared robust, but it was a house of cards.
A total house of cards. And this is the danger of opacity. It allows this invisible operational fragility to exist until a catastrophic deployment failure exposes it. It makes auditing for intent impossible when we can only audit the output.
Okay, so if opacity hides how the decision is made, the next major challenge is bias, which dictates which decision is made, and often unfairly. The system can be operating with, perfect transparency, but still be fundamentally flawed because of the data we feed it.
That's the core tension. AI systems learn from historical or imperfect datasets that inherently reflect our existing societal inequalities.
Historical lending practices, employment trends.
Criminal justice outcomes, you name it. When these datasets are used to train new models, the systems risk reproducing, or even worse, amplifying those biased and discriminatory outcomes. The system becomes a mirror reflecting the world's imperfections, and often magnifying them because of its scale and speed.
And we're not talking about malicious intent from the developers here, right? It's more about unintended consequences.
That's a critical distinction. It's often about well-intentioned software developers who just failed to ensure data equity. And the sources categorize the risks associated with this kind of residual bias into three main types, which is helpful for figuring out where we need to intervene.
Okay, so let's go through those three.
First, you've got input bias. This is the most common one. It's about problems with the data used to train the model itself. Maybe the data is incomplete, it's lacking representation for certain demographic groups,
Right.
or maybe it's historically prejudiced, reflecting old hiring norms that penalize certain genders or races. If your training data is missing 90% of a certain population, the model is going to be inherently biased against making accurate generalizations for that group.
Simple as that. Okay, what's second?
Second is system bias. This is more about flaws in the algorithmic design or the architecture of the model itself. It's a bit more abstract.
So not the data, but the math.
Kind of.
Mm-hmm.
For instance, think about how optimization functions treat different groups. A model might be trying to maximize accuracy globally, but in doing so, it accepts a significantly higher error rate for a small, underrepresented group.
So say misdiagnosing a rare disease that only occurs in 5% of the population.
Exactly. Because the cost of getting those 5% wrong is outweighed by the gains for the other 95%. That's an algorithmic choice that leads to a biased outcome.
And the third category, application bias, suggests that even a perfectly trained and designed model can still fail when you actually deploy it.
Absolutely. Application bias comes from how the system is actually used or deployed in the real world. A lending model that's fair in testing might generate unfair outcomes if, for example, it's only deployed in economically depressed areas where the overall data pool is different.
Or if the human operators interpret the results in a discriminatory way.
Precisely. The model itself might be sound, but its application environment is flawed.
And when these biases aren't dealt with, they lead to pretty significant ethical fallout. The sources use this framework, Ibotta, to summarize the core consequences, which I think is worth a closer look.
Yeah, that framework really helps us grasp the scope of the problem beyond just, technical error rates.
So let's break down Ibotta.
Okay, so the I stands for injustice. This is the discrimination, the unequal or unfair treatment based on factors like sex, race, age, economic status.
Like a facial recognition system that works flawlessly for lighter-skinned men.
But has a 40% error rate for darker-skinned women, which can lead to higher rates of false identification and, wrongful arrest for that group.
And the A stands for a loss of autonomy.
Right. Loss of autonomy is where users lose control or are sort of subjected to paternalism because they're relying on the technology. Think about personalized feeds on social media.
Sure.
If a system decides what information you see based on maximizing engagement, it limits your exposure to varied ideas. It effectively reduces your freedom to form independent opinions. Your choices are being managed for you.
And then there's T, for transformation of basic concepts and values.
This one's subtle but really profound. It happens when these AI metrics start to define or even replace human experiences. For example, replacing a complex human review of a teacher's ability with a single, simplified AI-generated performance score.
The score becomes the reality.
Exactly. The score transforms the complex reality of teaching into a measurable commodity, and then people start optimizing for the score, not for the actual educational outcome.
And finally, the last A in Ibotta is critical: gaps in accountability.
This is that dissolved or unclear responsibility that pops up when no single entity, not the data supplier, the model developer, the deployer, or the operator, can be held liable for the harm caused by a biased decision.
So if an AI denies a family a social benefit,
Tracing who is at fault can become a legal labyrinth. Was it the company that sourced the biased historical data?
right,
Or the government agency that blindly implemented the opaque system? This leads to injustice.
so it's clear that organizations have to establish these strong internal mechanisms like AI ethics committees and constant monitoring to try and get ahead of this.
Absolutely. And while the scientific efforts are robust, we see great measures to identify and mitigate biases, the sources lead us to a pretty sobering conclusion that's central to designing for trust. There are, as of yet, no measures to eliminate all biases in AI systems. We have to expect and learn to live with some unknown or residual biases, especially because they're trained on our own imperfect human history.
So the goal shifts from achieving zero bias, which is impossible,
Right.
to achieving maximum transparency and accountability about the biases that remain. We have to be honest about potential injustice and make those trade-offs between, say, fairness and efficiency transparent.
That's the key. Think about a healthcare diagnostic system. Maximizing efficiency might mean building a system that quickly screens millions of people. But what if that system, in its rush, performs slightly less reliably for a rare demographic group?
Like misdiagnosing a condition in people over 80 with comorbidities.
Exactly, you've just traded a small portion of fairness for a large gain in efficiency. A trustworthy system has to communicate that trade-off openly, so that human doctors know to scrutinize that high-risk group more closely.
Okay, so the third major trust challenge deals less with the machine's internal logic and more with our response to it. This is automation bias, and it feels like a serious systemic risk that can just subvert all our best intentions for safety.
Automation bias is this deeply ingrained tendency we have to over-rely on an automated system. We often favor the system's output, its suggestion, even when we have contradictory information or professional training or just simple common sense that tells us it's wrong.
We just default to the machine.
We default to the machine because we perceive technology as being inherently more objective or reliable than our own flawed human judgment.
And this moves beyond just poor performance and into safety-critical domains, causing real accidents.
Oh, the case studies demonstrate this so clearly. In aviation, automation bias has contributed to multiple real-world crashes. The sources describe these incidents where experienced pilots, professionals whose training is built on situational awareness, have ignored physical cues, like the visual height of runway lights or the actual feel of the controls, because the navigation display, the automated system, told them they were perfectly lined up for landing.
They trusted the screen over their own eyes.
They trusted the display's abstract data over their own eyes and judgment, with absolutely disastrous consequences. It's a terrifying breakdown of expertise. The system, which was intended to be helpful, actually degrades the user's self-confidence.
And that overtrust carries over directly into other fields, like healthcare.
It does. Radiologists, who are highly trained visual experts, have been shown in studies to over-rely on AI advice when they're assessing chest x-rays. They fail to catch errors that their professional training should have immediately detected, just because the AI had already given a seemingly confident diagnosis.
So the machine acts as an authority, and the human just defers.
The human defers critical thinking. They move from being a checker to being a passive acceptor.
Which highlights the great irony of our primary safety measure, the human-in-the-loop safeguard. We assume putting a person there solves the problem.
Right.
But if that person is susceptible to automation bias, the entire safeguard fails.
The sources explicitly state that just inserting a human in the loop cannot prevent all accidents or errors. The moment the human overtrusts, they cease to function as a true independent safeguard. So leaders have to recognize that automation bias is a systemic risk. It needs to be mitigated through training, and more importantly, through intentional design that compels interaction, not just a passive final sign-off.
That leads us perfectly into part 2, the solutions. So we've established blind trust is dangerous, total skepticism loses value. The goal is this intentional reliance or calibrated trust. How do designers get there? How do they move beyond just simple accuracy metrics to achieve that crucial calibration?
The strategic design goal is precisely calibrated trust. It means human reliance on the system aligns with the system's actual performance. We saw overtrust leads to danger. But conversely, undertrust leads to a loss of value.
Because the user just rejects helpful suggestions and does all the work themselves.
Exactly. It neutralizes the system's benefit.
What's really fascinating here is how the research is starting to quantify this. Traditionally, studies just focused on the AI's confidence score, but the sources highlight a new approach that looks at both human and AI capabilities.
This is a major shift in the research. Optimal human-AI team decision-making requires knowing not just the AI's confidence, its correctness likelihood, or CL, but also the human's correctness likelihood on that specific task.
Why both?
Because the goal is to identify complementary task instances, situations where only one member of the team, human or AI, is likely to be correct, and you need to make sure the decision defers to the one with the higher probability.
That's intuitive, but how do you model something as subjective as a human's correctness likelihood? I mean, you can't just wire up their brain.
That's the core innovation. It's done by approximating the human's decision-making model based on their past behavior. Cognitive science theory suggests humans adopt similar solutions for similar problems. So researchers can estimate a person's CL on a new task based on their performance on similar tasks in the past.
Can you give me an analogy for how that works?
Sure. Think of it like this. If you're an expert chef, and a new recipe requires chopping an onion, the system looks at your historical performance. It sees that 95% of the time, you dice onions perfectly when the recipe is French cuisine.
Okay.
but only 70% of the time when it's an unfamiliar Thai recipe. For a new French dish, the system assigns you a high CL, 95% on the onion task. For a new Thai dish, it assigns a lower one, 70%.
So the system basically approximates a set of decision rules that I, the human, am likely using.
Precisely. And it refines this rule set through interactive modification based on your input. By combining the human CL and the AI CL, the system can identify for any given task who has the higher capability.
And the studies show this actually works.
It's a powerful result.
Mm.
When humans are prompted to consider their own higher CL over the AI's lower CL, they exhibit significantly less overtrust in the AI's wrong recommendations.
That's incredibly practical. It moves beyond just showing the AI's confidence score, which people often ignore, to actively structuring the decision based on mutual capability. When the AI is wrong and its CL is lower than the humans, people are less likely to agree with it. Their trust becomes appropriate.
It promotes reliance on their own judgment when the AI's advice is flawed. And this shifts the relationship from, master-servant to effective collaboration, where the human understands their strengths relative to the machine.
So if the goal is calibrated trust, the operational mechanism has to be transparency. We need to crack open that black box, but not by exposing, arcane code or dense math.
Right.
It's really about aligning the user's mental model of the product with reality.
That's exactly the right way to think about it. Trust breaks down immediately when expectations are mismatched. If a user thinks the AI is full context of today's market, but it only used the last 4 hours of data, trust will be violated when it inevitably misses a key trend.
So designers have to explain the relevant workings in a way we can actually digest.
And the key is making sure the explanation is in context and useful, not just a technical data dump.
What are some of the specific design patterns that do this, that achieve this necessary visibility in a UI?
Well, the sources detail several tactics. First, in-context explanations. This means explaining how an output was generated right where the user sees it, without making them navigate away.
Like what?
For instance, a system tracking emerging tech might break down why it identified a trend as high growth by referencing recent patent spikes in that sector, or corresponding VC activity in the last quarter. The explanation is woven directly into the output.
So that turns a generic statement, this is a high-growth sector, into a grounded, actionable insight that the user can accept or challenge.
Exactly. Second, you have footprints or chains of thought. These let users trace the source trail, the step-by-step reasoning that led to a conclusion.
So you can see its work.
You can see the work. In a legal discovery tool, you might click on a conclusion and see the specific documents, the filters applied, and the synthesis steps the LLM used. This builds confidence that the process was rigorous. Third, citations. This is fundamental. Linking outputs directly to source data documents reports lets users verify it themselves.
But maybe the most counterintuitive trust-building tactic is designing for visible fallibility. We're taught in design to minimize error, to achieve seamlessness. And here we are saying we should actively show the machine's uncertainty.
This is a powerful pivot. Credibility often comes not from declared precision, but from consistency, data grounding, and clear boundaries. A system that overpromises and underdelivers damages trust immediately.
But a system that's honest about its limitations.
Fosters respect. So systems must avoid absolutes. Designers should use self-critiques like, this signal may be inflated, or prompt the LLM to use uncertain language like, this may suggest.
That's a huge distinction. It shifts the perception of the AI from being this infallible authority, which we know it's not, to being a transparent, if flawed, collaborator whose boundaries are clearly marked.
We see this principle applied really successfully in everyday tech, like wearable health trackers.
Right, like a Fitbit or an Oura Ring.
Exactly. Take Aura's readiness score. They don't offer medical diagnoses. They frame guidance as optional, and they consistently explain why a score changes based on transparent underlying data, sleep duration, heart rate variability, recovery metrics.
So by making the uncertainty visible and backing it with data, they support informed user behavior.
And trust emerges from that predictable guidance, not from some illusion of perfection.
Let's move to this idea that actively slowing the user down can be a positive design choice. We live in a culture that equates friction with pain and its removal with progress. The frictionless experience is the holy grail.
It is.
But the sources really challenge that, suggesting that designing for frictionless experiences risks designing out humanity.
That's the critical insight here. If we aim for seamlessness at all costs, we design out those moments of critical thinking and judgment that prevent automation bias. So the concept of productive friction is a deliberate pause, a cognitive resistance intentionally baked into the design,
To compel users to pause and think.
and prevent that default complacency that leads to dangerous over-reliance.
It's counterintuitive, but it makes sense. A runner needs friction to accelerate, not to slide out of control. We need friction points to pivot or apply judgment. So what does this intentional friction look like in practice?
We see three key strategies. First, point-of-output prompts. These are small delays, confirmation boxes, or nudges that compel users to review AI-generated content before finalizing it.
So before a system executes a large financial transaction suggested by AI,
A prompt asks the human, "Are you confident this strategy accounts for current market volatility?" It inserts resistance to combat anchoring bias, where users just mirror the AI's initial suggestion.
okay, what's second?
Second, suggestion boundaries. Making it explicitly clear when AI is offering an idea versus making a final, confident decision. Grammarly is a great example.
Oh, yeah.
It underlines a spelling or grammar suggestion rather than just auto-correcting it. That slight resistance, the need to click, allows the user to retain creative authority over the final text. It promotes collaboration over passive acceptance.
And the third strategy involves actively challenging the user, which is called cognitive forcing functions.
Right. Cognitive forcing functions, CFFs, integrate highly intentional friction to challenge underlying assumptions. This could be mandatory questions that pop up, like, what demographic segment is this result least likely to apply to, or could this be explained by noise?
So it forces you to use your own domain expertise.
Precisely, which is crucial for calibrating reliance.
Yeah.
And we have to recognize that friction has to be dynamic. Humans acclimate so quickly. What feels like a critical pause today might fade into the background tomorrow, just another routine click. Organizations need to monitor and adapt these friction points over time.
We've talked about the challenges and the design solutions. Now, let's widen the lens and look at the accountability structure, the role of human expertise, and the broader social cost of automation. This is about where responsibility ultimately shifts when the machine is at fault.
Right. And how we ensure a societal benefit.
So let's start with the role of the human in the loop, or HITL, and expertise.
We really need to redefine what human in the loop means. It's far more than just labeling data. It's a fundamental design approach that embeds human judgment, ethical reasoning, and nuance directly into high-stakes workflows like healthcare, finance, law.
It ensures human input happens before, during, and after an AI action.
And it recognizes that human insight remains indispensable. And this isn't just a best practice anymore. It's rapidly becoming a regulatory mandate.
Right, with things like the EU AI Act.
Indeed. Under foundational frameworks like the forthcoming EU AI Act, external human oversight is a requirement for high-risk systems. This oversight should minimize risks, with mandated methods like manual operation, intervention, overriding, and crucially, the human involved must be deemed competent.
Meaning they understand the system's limitations.
And are fully aware of potential automation bias and possess the authority to intervene immediately to prevent harm.
We talked earlier about how adjustable automation promotes calibrated trust. Why is that specific design element so powerful?
That's where the different bases of trust come into play. When a system allows for adjustable automation, giving the user the ability to change the level of automation, maybe move from fully automated to man-in-the-loop.
It increases what's called integrity or process-based trust.
Yes, the user perceives the system as operating with the right recipe, using a transparent methodology, allowing collaboration. This sense of agency and control is fundamental to building deep, resilient trust. If I feel like I'm controlling the tool rather than being controlled by it, I'm more likely to use it appropriately.
Beyond technical and regulatory expertise, the sources emphasize that true trustworthiness requires integrating the subjective, grounded knowledge of users and domain experts. They call it lived experience.
Lived experience is absolutely crucial for aligning AI systems with the nuanced realities of human users. For a long time, AI development has often treated users as abstract data subjects, reducing behavior to predictable patterns.
But that misses the contextual, tacit expertise people bring.
It does. For example, in healthcare, while an AI is great at pattern recognition on an X-ray, it often lacks experiential knowledge of the clinic, the patient's history, or the social context of their disease.
So what are the specific gaps that lived experience fills in medicine?
Well, health practitioners, through years of experience, possess expertise in navigating complex emotional scenarios, understanding trauma contexts, and identifying edge cases like adverse psychiatric drug reactions that current AI systems just struggle to replicate because they lack that experiential grounding.
So a conversational medical agent might fail not because it lacks information.
But because it offers decontextualized advice, it highlights the limitations of designing for narrowly anticipated needs without input from lived practitioner and patient experience.
And this principle applies even in educational settings, right?
Absolutely. In educational autograders, research showed a fascinating design failure. When the AI provided overall positive feedback, students were less likely to read the necessary detailed correctional feedback.
Even if the corrections were vital for learning.
Yes, the failure stemmed from overlooking the lived experience of students and instructors, where feedback dynamics are relational and pedagogical. The designers optimized for positive reinforcement, but that diminished the learning potential. True trustworthiness requires centering these expert and student perspectives.
So when we talk about designing for trust, we also have to address the inverse. The designs that actively exploit our vulnerabilities, often undermining autonomy for profit.
Yes, the digital well-being challenge and addictive design features,
Which are a subset of dark patterns.
a critical subset. These are interface and algorithmic features specifically designed to exploit neurocognitive vulnerabilities, especially around reward anticipation, to induce dependency-like behaviors. We see this in features like the infinite scroll mechanism, autoplay functions, and personalized recommendation feeds that just keep you continuously engaged.
These features aren't neutral. They're strategically engineered to prolong compulsive engagement.
And the regulatory landscape is finally recognizing this, especially with vulnerable populations like adolescents. New legislation is moving toward mandating anti-addiction by design,
Which shifts the duty of care to the platforms.
requiring them to intentionally prevent harm by introducing friction elements, conscious decision points, and visible time use reminders. These interventions create built-in negative feedback loops that dampen the reinforcing cycles of compulsive engagement.
And the erosion isn't just behavioral, it can be deeply cognitive, as shown by the fascinating case of the GPS paradox.
Oh, this is a great example. Navigation apps like Waze and Google Maps have earned extremely high daily trust because they save time and reduce stress. A massive gain in efficiency.
But there's a significant cognitive trade-off we rarely acknowledge.
There is. The sources explain that when we follow turn-by-turn directions, we predominantly use what are called response strategies.
Which means?
A response strategy involves simply memorizing a path, a series of steps like turn left at Main, turn right at Elm. This is contrasted with spatial strategies, which involve forming mental maps, learning landmarks, connecting to the environment holistically. The problem is, following GPS directions only activates the brain's response strategy.
So it limits our ability to build those crucial internalized mental maps. We get where we're going.
But we don't learn where we're going.
Yeah.
Exactly. And the spatial strategy matters profoundly because of its link to the brain. Spatial strategies, specifically map formation, correlate with high activity and even an increase in the size of the hippocampus.
And the hippocampus is the region of the brain associated with spatial navigation and memory.
And long-term episodic memory. Conversely, degradation of the hippocampus is an early indicator of Alzheimer's and other cognitive decline.
Wow. So the convenience gained by over-relying on GPS translates directly to a reduction in the brain's exercise, potentially impacting a vital region linked to long-term memory.
The trade-off is clear. Immense convenience for the subtle, long-term loss of a valuable human cognitive skill. We lose our spatial intelligence because the automation has replaced the necessity for our brain to do the work. It forces us to ask, what is the optimal user experience? It's not just maximizing efficiency, it's balancing that against the irreplaceable value of the human skills it slowly erodes.
So the urgency of these challenges, from bias and opacity to skill erosion, has created this pivotal moment in 2024 and 2025 where global regulation is really moving from theory to tangible action.
This is the era of AI governance. And the cornerstone of this shift is the risk-based approach, which we see exemplified by the EU AI Act. It's setting a global precedent.
And that's the tiered system.
Right, a tiered system based on the severity of the threat to safety and fundamental rights. The first category is prohibited risk. These are systems that pose an unacceptable risk and are just completely banned. This includes systems that use manipulative techniques to exploit the vulnerabilities of individuals like children or people with disabilities to distort their decision-making.
What's a specific example of a prohibited system?
A prime example is the ban on certain systems of real-time, remote, biometric identification in public spaces, especially those that categorize individuals based on protected characteristics like race or political opinion. It also prohibits general social scoring systems that penalize citizens because they erode autonomy.
Then you have the next level of concern, high-risk systems.
These are systems that pose significant risks to fundamental rights or health and safety, and they require the most stringent controls.
So rigorous testing, transparency.
Mandatory transparency measures, human oversight like we discussed, and establishing a formal risk management system throughout the model's entire life cycle. This category impacts crucial sectors like healthcare, employment, and transportation.
On the organizational side, how are companies addressing this difficulty of assigning responsibility for AI errors when the tech is so complex?
They're strengthening internal and external mechanisms because they recognize that responsibility is now organizational, not individual. Internally, this means formal AI ethics committees, cross-functional oversight teams with engineers, lawyers, and ethicists, and continuous monitoring systems.
Baking responsibility into the culture, not just bolting it on at the end.
Exactly. And externally, companies are recognizing the need for independent checks.
Like audits and red teaming?
Yes, through external audits, red teaming exercises, and third-party evaluations. Red teaming is crucial. It involves bringing in external experts to probe the system, specifically looking for failure modes and vulnerabilities, like the clever Hans effect, that might not be apparent to the internal developers.
Finally, let's bring this back to the consumer. How is all this affecting consumer trust in brands, especially with the rise of AI-fueled fraud and deepfakes?
Consumer confidence is demonstrably eroding. The sources note a really striking statistic. Only 17% of consumers fully trust organizations to manage their personal identity data.
That's incredibly low.
It is, and this decline is fueled by AI-enabled fraud, where threats are becoming more persuasive, personalized, and harder to detect. It's leading to a pervasive trust-nothing era in digital interactions.
So safeguarding data privacy and proving trustworthiness is now moving from a simple compliance task to a competitive advantage.
Absolutely. The brands that will thrive are those that make trust their top priority and can demonstrate it proactively. This means implementing strong, seamless authentication biometrics, multi-factor authentication, and crucially providing transparent, clear explanations about how they use and secure consumer data. Trust has to be explicitly earned, not assumed. So as we synthesize this deep dive, I think the main takeaway is clear. Trust in AI is not a fixed quality. It's a dynamic, intricate construct that requires technical rigor, transparent communication, and really intentional design.
Yeah.
We have to acknowledge that building trustworthy systems involves far more than just technical sophistication. It demands a principled approach rooted in human values, recognizing the inevitability of residual bias and the inherent fallibility of these complex systems.
And we must strive for calibrated trust. We need to design systems that are honest about their limitations and encourage human review and intervention rather than tempting us into this dangerous over-reliance through seamlessness. The path forward involves designing resistance, that productive friction, to safeguard our autonomy and preserve our cognitive skills.
We can't design out every single error.
No.
So we have to design how we respond to those errors.
The historical standard of design was all about minimizing user effort and achieving seamlessness, assuming that frictionless equals better.
Right.
But given the complexity and the consequential risks of modern AI, the new imperative for trustworthy design might just be the opposite: visible fallibility, showing users how a system handles mistakes and making uncertainty visible. That's the key to future dependability.
That's a powerful final thought. Showing users the sources, displaying the uncertainty score, asking them to pause and review, that builds real lasting trust, far better than any facade of perfect accuracy.
So the provocative thought for you to carry forward is this. The next time you use an AI tool, what kind of intentional, productive friction will you look for that proves the system is designed to preserve your autonomy and encourage critical thinking, rather than merely prioritizing speed and convenience?
A great question to end on.
That's all for this deep dive. We hope this gives you the grounding you need to navigate this age of intelligent technologies with properly calibrated trust. We'll see you next time.